Patellar tendinopathy often feels manageable during the flight of a jump, only to create a sharp pain ceiling the moment the foot touches the ground. Upon landing, the patellar tendon acts as an emergency braking system, absorbing massive amounts of kinetic energy in a fraction of a second. This deceleration creates extreme mechanical demand. Peak force traveling through the patellar tendon during a single leg landing frequently exceeds 8 times an athlete's body weight. A healthy tendon acts like a stiff spring to absorb and rebound that force. In a tendinopathic state, the tissue lacks the mechanical competence to safely distribute that volume of energy. This failure is a structural limitation. No amount of willpower can override the physical boundaries of a tendon that cannot support the load. Resuming plyometrics is only possible after building new tissue capable of managing these high-velocity forces.
To truly address this persistent performance deficit, we first have to examine the microscopic cellular architecture of the tendon itself. An injured tendon is dominated by type 3 collagen. This tissue is disorganized, loosely packed, and structurally fragile. Athletic performance requires the stiff, linear strength of type 1 collagen. Type 3 collagen lacks that alignment, acting more like a frayed rope than a steel cable. Rest and anti-inflammatories target the chemical signal of pain, but they do not address this underlying structural breakdown of the load-bearing fibers. Experiencing heavy, controlled mechanical strain is the specific biological cue that forces the human body to physically remodel this damaged tissue. The goal of rehabilitation is the systematic conversion of disorganized type 3 tissue into mechanically competent type 1 collagen. Driving that conversion requires a protocol with enough load to trigger remodeling. This is heavy slow resistance, or HSR. This graph tracks the 2009 Kongsgaard trial, comparing corticosteroid injections, eccentric-only training, and heavy slow resistance. By 12 weeks, all 3 groups reported symptom improvement and pain reduction. However, at 6 months, the corticosteroid group relapsed entirely, returning to baseline pain levels. While injections masked the pain, they failed to provide the mechanical stimulus needed to fix the structural problem. Long-term follow-up at 52 weeks showed that HSR was more durable than older eccentric-only protocols. At 1 year, patient satisfaction reached 100% in the HSR group, outperforming other loading strategies. Biopsy data confirmed the reason for this success. HSR physically increased the concentration of organized type 1 collagen. Because it produces measurable structural remodeling, HSR has become the clinical standard for patellar tendinopathy.
While the research is clear, the effectiveness of HSR depends entirely on how the sets are executed in the gym. Tendon adaptation is driven by cumulative time under tension, not just the peak weight of a single repetition. Consider these 2 tempos. A standard rep takes 2 seconds. An HSR rep requires a strict 3-second eccentric and concentric phase. Across an 8-rep set, standard tempo gives 8 seconds of tension, while HSR provides 48 seconds, delivering the mechanical signal for cellular adaptation. If you move the weight quickly, you are having a standard workout, but you are not providing the tendon with the specific stimulus it needs to heal. This requires a stopwatch on the bench and a metronome in your ear to ensure every rep hits the target. Protecting the slow tempo is mandatory. If you cannot maintain the 6-second count, you must reduce the weight on the bar. The heavy load provides the cue, but the slow tempo ensures the tendon receives the signal. To optimize this signal, the loading dose is structured over a 12-week progression. Weeks 1 and 2 focus on building initial tolerance with 3 sets of 15 repetitions at 70% of your 1-rep max. From weeks 3 through 8, the repetitions drop as the load on the bar rises toward 80%. By the final month, the program transitions to single-leg dominant movements at 85% of your maximum capacity. These percentages must be based on an accurate 1-rep or 5-rep max test. If the baseline is wrong, the physiological dose will be insufficient. The frequency of these sessions is dictated by the collagen synthesis cycle, which peaks and then returns to baseline over 48 hours. Loading the tendon every day interrupts the synthesis. Recovery time is when the actual tissue remodeling occurs. Sticking to 2 or 3 sessions a week ensures each loading event happens exactly when the tissue is ready to adapt again. The purpose of these 12 weeks is to prepare the tendon for the transition into explosive Phase 3 plyometrics. This requires closing the strength gap between the injured leg and the healthy one. We measure this progress using the Limb Symmetry Index, or LSI. The injured leg must reach at least 90% of the strength of the healthy leg before it can safely manage energy storage loads. The final exit criteria is a single-leg HSR squat at 75% of your max, tolerated for 3 sets of 8 at a strict tempo. Achieving this means the tendon has developed the cross-linked stiffness and pain modulation required for impact. This strong structural foundation allows you to safely return to explosive movements without triggering a new cycle of pain. By following the Kongsgaard protocol, you are building a tendon that can sustain high-level performance and absorb the forces of the game.